In this example problem, we're going to create a simple moment curvature diagram for the section shown below. We have a 16-inch by 24-inch rectangular section with 4 number 9 bars located on the tension side of our beam. We have an F'C of 5 KSI, grade 60 reinforcement, so our Fy is 60 KSI. We have stiffness of our steel, 29,000, 1.5 inches cover, and number 4 ties to give us the location of our bars, which we'll calculate. The 4 points that we're going to calculate for our simplified moment curvature diagram are our immediately before cracking point 1. To find this point, we're going to use our uncracked transform section properties, and we're going to calculate our M cracking and our curvature before cracking. What we'll do is we'll determine the stress, or we'll determine when the stress equals our concrete tensile strength in the bottom of our section, and find the moment to cause that point. The next point we'll find is our immediately after cracking point, or point 2. Our section is going to go through some inelastic rotation as the concrete stress is transferred from our concrete to our steel. And to find this point, we'll use our cracked transformed section properties, and we'll find our after cracking curvature. We'll then find the end of our elastic region, point 3. And we're still going to use our cracked transformed section properties to determine our yield moment and yield curvature, so the point when our steel equals Fy, and also the point when the concrete stress at the extreme compression fiber equals 0.7 F'C. These are the 2 points that will signify or cause our section to go inelastic. The last point that we'll find is our nominal moment capacity, and to find this point we'll use our rectangular stress block approximations to calculate Mn and Phi(n). So the first thing that we're going to do is we'll calculate some generally required properties that we'll use for multiple points. The first is our EC. So our EC here is 57,000 times the square root of 5,000 psi, all divided by 1,000 pounds per kip to give us 4,031 KSI. The next point, or the next value we'll calculate, is our modular ratio, which is the way that we transform our steel into an equivalent concrete area. So here, our modular ratio is 29,000 divided by 4,031 KSI, which will give us a value of 7.2. Next, we can calculate our D. Our D is our overall height, 24 inches, minus our cover, 1.5 inches, minus the diameter of our stirrup. Our number 4 ties have a diameter of 4/8, or 1/2 inch, and then minus half of the diameter of our longitudinal bars, so our number 9 bars, 1.128 inches. And this will give us a value here of 21.44 inches. We'll now calculate our immediately before cracking point. And we can do this by using our uncracked transform section properties, which we'll need to calculate. We found our depth of steel already to be 21.44 inches on our previous slide. We can then find our area of steel, which we have 4 number 9 bars, which a number 9 bar has an area of 1 square inch. So we'll get 4 square inches as our area of steel. We can then break our section up into a number of different areas to find our transformed centroid. So we'll have our concrete section, and then we'll have our transformed steel section as our 2 different areas. And the centroid is just going to be equal to the summation of these areas times the distance from the center of the area to the top, divided by the summation of these areas. So for us, we'll have our yt equal to our base times our height, 24 inches, times our height divided by 2, plus our n minus 1 times our steel area, times the distance from the top to the center of this area, which is just equal to d. And then we'll divide all this by the summation of our areas, so 16 times 24 plus 7.2 minus 1 times 4 to give us our distance from the top to the centroid of our transformed section, transformed uncracked transformed section, to be 12.6 inches. We can then use our parallel axis theorem to calculate our I uncracked transformed. So we'll have the I plus a times d squared component for our concrete section and our transformed steel. And we're going to neglect the I component of our transformed steel. So we can then calculate it, and we'll find our I uncracked transformed is 16 times 24 to the third divided by 12 plus 16 times 24. So our area times our d squared component. So the centroid of our overall section, 12.6 inches minus 24 over 2, and all this squared, plus 7.2 minus 1 times 4. So our area of our steel times our d squared component, 21.44 minus 12.6 squared. And we'll get our I uncracked transformed to be equal to 20,819 inches to the fourth. So this is the value that we'll need moving forward. We can now calculate our cracking moment using these section properties. And to do so, we'll first need to calculate the concrete tensile strength. We're going to use 7.5 square root F prime C because we're looking at the flexural tensile strength. So we'll have 7.5 times 5,000 psi divided by 1,000 pounds per kip to give us 0.531 KSI. We can then find our M cracking, which will be equal to our FT 0.531 KSI times our I uncracked transformed 20,819 inches to the fourth divided by our overall height, 24 inches minus 12.6 inches, which will give us a cracking moment of 966.1 kip inches. Note that this distance on the bottom is the distance from our centroid to our extreme tension fiber, where cracking will first occur. So then we can find our before cracking curvature, which will just be equal to our strain at the bottom divided by the distance from our centroid to the bottom of our section. So for us, we'll have our strain at the bottom is 0.531 KSI divided by our stiffness, 4,031 KSI, and then divided by 24 inches minus 12.6 inches, which will give us a before cracking curvature of 1.15 times 10 to the negative fifth. Finally, we can calculate our stress in our steel. And our stress in our steel is going to be equal to 29,000 KSI times our curvature, 1.15 times 10 to the negative fifth. And sorry, the units here are radians per inch. And then times 21.44 inches minus 12.6 inches. So the distance between the centroid and the centroid of the overall centroid of our section and the center of our steel. So we'll get a stress in our steel of 3 KSI before cracking. So you can see that before cracking, our steel is not significantly engaged. And we'll look on the previous or the next slide to see how the stress increases after cracking occurs. The next point that we're going to find is our immediately after cracking moment in curvature. So we know that our moment's going to stay the same, so now all we need to calculate is our curvature. And we'll calculate our curvature based on our cracked transformed section properties. To find the depth of our neutral axis, we can sum the areas times the distance to the neutral axis of all of our areas in compression, and set it equal to all of our areas in tension. So here we have our uncracked concrete as our only compression component, and we can note that we neglect our cracked concrete, so we're neglecting all of our concrete in tension. And then our second area below the neutral axis is our transformed steel. And note that because our steel isn't going through an uncracked concrete section, we don't need to take out an area of steel. So we just have N here. So N times our area of steel. So we have our two components, and now we can solve for KD. So we'll have our KD equals B over 2, so 16 inches divided by 2 times KD squared minus 7.2 times 4 square inches times 21.44 minus KD. If we, this will be a quadratic expression, so we can set it up 8 KD squared plus 28.8 KD minus 616.9 will be equal to 0. And we can solve for KD using the quadratic equation, and we'll find our KD equal to 7.2 inches. So the depth from the top to our neutral axis where we have 0 strain. Next, we can use this KD to calculate our cracked transformed moment of inertia. And again, we're going to use parallel axis theorem to sum all of our I components for our different components of our cross-section plus AD squared. And we'll again neglect the I component for our steel. So plugging in our KD to our I cracked transformed expression, we'll have 16 inches times our KD, 7.2 to the third, divided by 12, plus 16 times 7.2 times our distance, 7.2 divided by 2 squared, plus 7.2, which in this case is our N, times 4 inches squared, times 21.44 minus 7.2 squared. And this will give us an I cracked transformed equal to 7,823 inches to the fourth. And we'll use this I cracked transformed to calculate our curvature after cracking. The moment's going to be the same. So our M cracking here is going to be the same. So now we just need to find our after cracking curvature. And we can find it just using our curvature equals M over EI expression. So our moment here is going to be 966.1 kip inches, which we found earlier in this example. Our E, 4,031 KSI, and our I cracked transformed is 7,823 inches to the fourth. So we can find our curvature here to be 3.06 times 10 to the negative fifth radians per inch. We can, so this would make our second point on our moment curvature diagram with this curvature and our cracking moment of our moment of 966.1 kip inches. We can then use this curvature and our KD and our D to find our steel stress and the concrete top fiber stress. So our steel stress is just equal to our modulus times our strain, where our strain here is equal to our curvature times the distance between the neutral axis and the centroid of our steel. So here we'll have a steel stress equals 29,000 KSI times 3.06 times 10 to the negative fifth radians per inch, and then times our D here, so 21.44 minus our KD, 7.2, would give us a steel stress here of 12.7 KSI. So we can see that our steel stress goes from 3 KSI before cracking to 12.7 KSI after cracking. You can see that this is our the effect of our stress being transferred from our uncracked concrete to our steel after cracking. We can also calculate our concrete top fiber stress. So here we're finding our FC at the top. And this will be equal to our EC, 4,031 KSI, times our curvature, 3.06 times 10 to the negative fifth radians per inch, times our KD, 7.2 inches. And this will give us a stress of 0.88 KSI. So that's our maximum compressive stress in our concrete. And our analysis here is going to be valid until either our steel reaches yield or our concrete stress in the top fiber reaches 0.7 F prime C. This is when our material properties are going to result in our section behavior going nonlinear. But here we're below these values, so our analysis is okay. Our cracked transformed section properties are valid until either our steel or our concrete leads to material behavior leads to our section going inelastic. So either when our steel reaches yield or when our concrete stress in the extreme compression fiber exceeds 0.7 F prime C. So here we're going to find the end of the elastic region by checking both of these points. The first point that we can find is our yield curvature point. And we're going to be able to use our cracked transformed section properties here. So the first point that we can check is our point when our steel yields. So we'll find our yield curvature equal to our yield stress, 60 KSI, divided by our steel modulus, 29,000 KSI, times D minus KD, 21.44 inches minus 7.2 inches. So we'll get a yield curvature here to be equal to 1.45 times 10 to the negative fourth radians per inch. We can use this and our curvature equals m over EI expression rearranged to find our yield moment, which will be 1.45 times 10 to the negative fourth radians per inch times our EC here, 4,031 KSI, and our I cracked transformed of 7,823 inches to the fourth. And this will give us a yield moment equal to 4,571 kip inches. Now we need to compare this point with our point when our concrete concrete stress in the extreme compression fiber reaches 0.7 F prime C. So we'll find the curvature and moment for this point. So we have our curvature here of 0.7 times 5 KSI divided by 4,031 KSI. So this gives us the strain at the extreme compression fiber. And then we divide again by KD, 7.2 inches, to give us the curvature at this point, which will equal 1.21 times 10 to the negative fourth radians per inch. So we can then find, and we'll add in 0.7 there, but we can then find our moment when our stress at the extreme compression fiber reaches 0.7 F prime C. Again, using our curvature equals m over EI expression rearranged for m. So our moment here is equal to our curvature, 1.21 times 10 to the negative fourth radians per inch, times our E, 4,031 KSI, and then times our I crack transformed, 7,823 inches to the fourth. And we'll find our moment here when we have 0.7 F prime C in our extreme compression fiber to be equal to 3,821 kip inches. We need to compare the two moments now, and we can see that our moment when our concrete in the extreme compression fiber reaches 0.7 F prime C is lower than our yield moment. So this is the point that controls. So our MY point is fictitious. The last point that we're going to find is our nominal capacity. And to find our nominal capacity, we're going to use a rectangular stress block approximation. So with our nominal capacity, we no longer have linear section properties, so we can't use our transform section properties anymore to transform our steel or relate our steel to our concrete. And here we need to start from equilibrium, and we start with tension equal to compression. Our tension component is ASFY, and our compression component is just our rectangular stress block force here. If we had compression steel, we'd add it on the compression side. If we had another layer of steel somewhere in our tension region, we could add it on the tension side. But here we can we'll assume that our steel is yielded, and we can solve for our C. So our C is equal to our AS, 4 inches squared, times FY, 60 KSI, divided by 0.85 times 5 KSI times our B, and times beta 1. So our beta 1 we can find using the expression shown here from ACI, which will be equal to 0.85 minus 0.05 times 5 KSI minus 4, which will equal 0.8, and this is greater than 0.65, so we know our beta 1 value. So 0.8 here. And we can then find our C equal to 4.41 inches. We can then sum our moments about the centroid of our compression block, and we'll have our AS Fy, so 4 inches squared times 60 KSI times our lever arm, which will be 21.44 inches minus 0.8 times 4.41 divided by 2, which will give us a moment here equal to 4,721 kip inches. We can then also find our curvature, which will use our strain at ultimate and distance C to our neutral axis. So we'll find our curvature to be 0.003 divided by C, 4.41 inches, which will give us a curvature here of 6.80 times 10 to the negative fourth radians per inch. And the last thing that we need to do is we need to check the strain in our tension steel. So we assume that it yielded, so we need to check and make sure that it yielded. So we'll have our 0.003 divided by C, 4.41, times D, 21.44, minus 4.41, will give us a strain here of 0.0116. So this is greater than our yield strain. And it's also greater than 0.005, which is our tension controlled limit for ACI to ensure that we have a ductile failure. So we know that our assumption is correct. So then we have our curvature and our moment for our nominal point. Shown here is a summary of all of our results from this analysis. So you can see our 4 main points: our before cracking curvature with our cracking moment, our after cracking curvature with our cracking moment, our point when our section goes inelastic. So here, where our concrete reaches 0.7 F prime C in our extreme compression fiber, and then finally our nominal moment and curvature at nominal. And this makes up our simplified moment curvature diagram for a reinforced concrete section.